Okay, so in the last lecture, I showed the solution to the physical state conditions, and it's of this following form. Organize my chokes. So the physical state. So we have the irrationalities are acting on the Hilbert space. And then there is also L bar acting on the left mover with the same commutation relations. B is a space-time dimension. Okay, and so this describes the map from two-dimensional worksheet to one time d minus one spatial dimensions, and the map is given by this function f, which I take to be a dynamical variable, massless-free scalar fields on the worksheet. Okay, and the Hilbert space consists of creating oscillations like that. Acting on the vacuum. So this is the right mover. And these are left movers. And the physical Hilbert space is given by element of H subject to the condition that Ln minus delta N 0 is 0. Annihilate this for N positive or 0. Modulo the equivalence class that we identify two states related to each other under action of the author algebra for N greater than or equal to 1. Okay, this condition means that we have Ln annihilate psi for N greater than or equal to 1, and you have L0 minus 1 psi is equal to 0. Okay, and but I have to also add that we also have the same condition for Ln bar minus Ln 0 psi is equal to 0 for N greater than equal to 0. And also we also identify plus N minus N bar like that. Okay. In the last lecture, one of the things I did was to show that you need this normalization to be, this shift to be 1 in order for the, so we, in the last lecture, we require the condition. If you require consistency between light cone and conformal gauges. Then first of all, so if you have this to be some constant A, then you find that first of all, A should be equal to 1. And the second is that D equals 20. Okay, so this is what we show. I haven't shown that this is necessary and sufficient. This can be shown, and if I have time, I will go. I will do that. So far, what I have shown is that by checking solution to these equations for the first two, first the ground state, first excited state, and second excited state, then equivalence of these two gauge conditions leads to these conditions. So this can be interpreted in various different ways. One way to interpret it is that these conditions are needed in order for conformal gauge to give rise to a spectrum which is physical. That is that it has no negative normal states, etc. And another way to see it is that the light cone gauge apparently breaks Lorentz invariance. But if you are in these conditions and satisfy these conditions, then you can actually restore the Lorentz invariance even in the light cone condition. So this is what we did. And in the last lecture, we only looked at solution to these equations, the right moving part, but we should also remember that we have this left moving part. So we can combine them to understand what the physical spectrum is. So let's first do that. So let's look at the ground state. Well, ground state is easy because the ground state is a vacuum state subject to the condition with momentum P. So you have these two conditions. And so L0 is equal to 1/2 of P squared plus excitation. And but for ground state, there are no excitations, so N equals 0. So that means that P squared is equal to 1. So this is a scalar with mass square to be equal to -1. Okay, so this is, as I said, is a tachyonic. So this shows that the bosonic string is pathological. So the first excited state consists of states which are of this form. You excite right moving oscillations and left moving oscillation like that. We need same number of oscillator for the left mover and right mover because you have to satisfy this condition. So this condition, this condition in particular requires that L0 minus 1 psi is equal to 0. L0 bar minus 1 psi is equal to 0. But L0 is equal to 1/2 of P squared plus number of right moving excitations. So you count the number of excitations and that's N. So that basically determines the mass of the corresponding particles. L0 bar is the same 1/2 P squared because there's common momentum, center of mass momentum for the left mover and the right mover. And then there's N bar. So this N bar counts the number of left moving excitations. So if I say take difference between them, then you have L0 minus L0 bar acting on psi is equal to 0, but L0 minus L0 bar is N minus N bar. So that means that physical state needs to satisfy N equal N bar, called the level matching condition. So physical state should have the same number of excitations for the left mover and right mover. So therefore, the first excitation should be of this form. Okay. I have also shown you last time that P squared is equal to 0 in this case, and you can see that because L0. So L0 is P squared plus N, and N is 1 in this case, so cancel 1, so P squared has to be equal to 0. So these are massless. So you have massless tensor in the first excited states. Mu and nu are not particularly symmetric or unsymmetric. under the Lorentz transformation in 26 dimensions, so mu goes from 0 to 25, you can decompose this tensor into irreducible representation of Lorentz symmetry. So you can decompose that into symmetric tensor, unsymmetric tensor, and trace form. Okay, so it's useful to do that decomposition. So general state, therefore, is of this form. So linear combination of this versus these are different types of indices. Mu excite alpha direction, generate right moving excitation. Mu is in the direction of left moving excitations. So this state is not symmetric in mu and mu. So this coefficient in mu does not have particular excitation. So E mu, which depends on the momentum, can be decomposed into symmetric part, symmetric traceless part. So, and then unsymmetric part. And then trace part. So unsymmetric part by definition is unsymmetric, so that is this is equal to minus E mu, unsymmetric. And the symmetric traceless part, so I write ST for short. So this is unsymmetric. So ST part, symmetric traceless part is symmetric. And then traceless, meaning that eta mu nu, E mu nu, symmetric traceless is equal to 0. Okay, so you can decompose this state into symmetric traceless part and that symmetric part and trace part. So it turns out that these guys are gravitons. So this one is a graviton. And this is massless unsymmetric tensor field. And these are regarded nowadays as a candidate for dark matter, potentially. Well, not in bosonic string. Bosonic string is pathological, but the corresponding superstring theory, the excitation list type are very good candidate for dark matter in the universe. With some more elaborations, you need to, of course, start from superstring theory and construct a setup which is actually we can use to describe our universe. But once that is achieved, then the excitation of this type can be. So there is actually a growing interest in the light dark matter. Earlier in this century, many we call phenomenological particle physicists interested in particle high-energy theory directly relevant to experiment and observations. Thought that one of the leading candidates for dark matter were supersymmetric particle, which can be discovered at LHC. And but the LHC didn't discover it, so that it's not very sort of very difficult to regard that as a candidate. The more growing interest in another type of dark matter, which has very light masses, and this can be a very good candidate for that. This is called dilaton. And this is very important. This also plays a very important role. This actually adjusts the coupling constant of string theory. So strings. So far we have studied string theory freely propagating in space-time, but they can interact with each other. They can merge. They can go around loops and do all kinds of things. So you have to, in order to actually calculate physical amplitude, you have to calculate analog of Feynman diagram in string theory. And the string coupling constant control the strength of these interactions. On the other hand, one of the very important features of string theory is that it does not have any adjustable parameters. So usually, if you write down the theory, then it has parameters in defining cells. So for example, if you have Maxwell theory, then there is a electric charge for electrons, for example. You also have this thing called speed of light. There are various constants. And Newton's law of universal gravitation has Newton constant. Now, there is things called natural unit where you actually regard Newton constant and Planck constant and the speed of light to be 1. And in that unit, in that natural unit, we can express every physical quantity in terms of dimensionless numbers. And it has been speculated that, well, first, so if we write down the fundamental equation of physics, should that have any additional dimensionless parameter or not? And so, for example, people like Einstein speculated that fundamental law should not have any adjustable parameter, it should be uniquely determined. We don't know yet, but what I can say is that in string theory, at least, there are no such adjustable parameters. That every parameter in the series are expectation value of some dynamical field. And so it can be varied. So for example, it can have time dependence or space dependence. And this is a kind of example. Oh, by the way, so in fact, this is a kind of statement that you can actually prove more generally for quantum gravity. So at least in the in the context of ADA-CFT correspondence, where we have actually a sort of fundamental principle in definition of quantum gravity in negative cosmology, the gravitational theory with negative vacuum energy, we can actually prove by mapping statement in gravity into the dual conformal theory that there are no adjustable parameters in gravitational theory. So maybe I'll discuss that in the second quarter when I introduce ADA-CFT. But this is the first instance where this appears. That if you calculate the Feynman diagram of string theory, there is a coupling constant that controls the strength of interactions. It's called the string coupling constant. And the value of the string coupling constant is determined by expectation value of this field. Megaton is a scalar field. The massless scalar field. So if you have a massless scalar field, then that field may have expectation value, the vacuum expectation value. Because if you have massless scalar field, let's call this phi, the massless scalar field satisfies this equation motion. So you can have non-zero vacuum expectation value for the scalar field because this condition is compatible with this equation. If the scalar field has a mass, you cannot adjust the expectation value. But if the scalar field is massless, you can have continuous choice of vacuum expectation value. And so Diraton is a massless scalar field because it's one of the first excited spectrum. And so therefore it can have expectation value, and this expectation value adjusts the string coupling constant. So for example, you can compare interaction between two strings propagating without interaction versus two strings combined together and then detach. So if you do the Feynman diagram, you have to sum over this. But then there is actually a string coupling constant square, which determines the relative strength of these two processes. And this string coupling constant is determined by exponential of phi, where phi is a Dirac field, which appears over here. Okay, so that's the spectrum. And we can also see that this identification of physical state translates into gauge symmetry. So let's see how it goes. Okay, so I said that in the first excited state, we have this state of this form. Okay, so now I said that any state that can be written in this way, so we should be able to add that physical state, and then you should describe the same physical state. So what does that mean? Well, suppose, for example, you multiply n minus 1. Well, this already have one excitation, so this gains n equal 1. So we can't have any oscillations over here, but for the left mover, we can have oscillators, so it should be of this form. Okay, so what is L minus 1? L minus 1 is summation, well, in general, Ln is alpha n minus m, alpha m. So L minus 1 is this. So that is equal to alpha minus 1, alpha 0, plus alpha 0, alpha minus 1. Okay, so So alpha 0 is P, essentially something proportional to P. So therefore, one can twice be able to write this as something proportional to P mu, alpha minus 1 mu, alpha minus 1 bar mu, acting on the way. So that means that the physical state of this form should be invariant under shift of state like that. So this amounts to, so that means that we should be able to add P mu nu, alpha minus 1 mu, alpha minus 1 bar mu 0 to lambda mu P mu, alpha minus 1 mu, alpha bar mu, acting on the value. And this state is the same as E mu nu, alpha minus 1 mu, alpha minus 1 by mu, acting on the value. These should have the same, this should be the same physical state. So that means that physical states are characterized by this polarization for the first excited states should be equivalent to the physical state with this polarization, E mu lambda mu, for any lambdas. Okay, so this is in a momentum basis. So P, so E is in the momentum parameterization, but we can also write it in the so this is the Fourier transformation. And you can write E tilde mu nu of x to be the momentum integral of E mu nu P. Then in the Fourier mode, this is equivalent to E mu nu tilde x plus del nu lambda mu. So you identify these states. Okay, so let's see how it looks like. So for example, if I consider symmetric part, symmetric traceless part, which is equal to E mu nu plus E mu nu minus, so let's say we need to calculate 2D over eta mu nu, eta rho sigma, E tilde rho sigma. I subtracted this piece because if I take trace of this, you get trace of this, you get trace of this, so you get twice a trace. If I take trace of this, you get D because you have D dimension. So 2D cancels this. And so this is trace. So by definition, this is symmetric traceless. And so this symmetric traceless tensor will then transform under this transformation. E mu nu ST is equivalent to E mu nu tilde ST plus del mu lambda nu plus del mu lambda mu minus 2D eta mu nu del lambda. Okay, so this is how symmetric part transforms. This is exactly the gauge transformation of the graviton or diffeomorphism on the graviton. So you know that, so what is graviton? Well, the way that graviton appears in Einstein's theory is that you first write down the Einstein-Hilbert action, which there is 4 pi here, d-dimensional Einstein equation with the Einstein-Hilbert action. And then what you do is that, well, the Einstein-Hilbert action is a function of the metric. You perturb this metric around flat space with small h mu nu, and then write down the equation motion for h mu nu. So in the appropriate gauge, h mu nu satisfied is basically the massless. H mu nu is a massless symmetric traceless tensor. And but then an important feature of Einstein theory is it's a general relativistic, which is a series invariant under diffeomorphism, change of coordinate. So you can still be able to change x to be x mu plus epsilon lambda mu of x. And under the coordinate transformation, the action should be invariant. So therefore, the equation of motion for massless symmetric traceless tensor, rank 2 tensor, should respect this symmetry. And this symmetry on this h mu nu acts exactly in this way, where E is replaced by H. So we can identify E tilde mu nu is equal to H mu nu. So we see that from the first excitation of string, symmetric traceless part behaves exactly like graviton. And when you see something which looks like graviton and smells like graviton, must be graviton. And this is actually exactly what Steven Weinberg showed in 1965. So in my first lecture here, I quoted Weinberg-Witten theorem. And what that theorem said was that the theory has massless spin-2 particle. You cannot have non-trivial energy momentum tensor. So Weinberg actually proved a lot of interesting theorem about quantum gravity in the 60s. He was primarily a formal theorist that interested in formal property of theory. His most important work, however, turned out to be the construction of model of elementary particle, of which he got Nobel Prize. So it's very interesting. It was just one paper which he wrote about phenomenology that he won Nobel Prize. But most of his work was actually about the theoretical structure of quantum field theory of gravity. And there was another important paper Weinberg wrote, which had phenomenological relevance, which was a prediction of the value of cosmological constants. But that's the status of validity of his argument is still being debated. So anyway, so there is a very important paper by Steven Weinberg. This is a physical review of 138, 1965, B988, I think. For the photons and the graviton in perturbation theory, derivation of Maxwell's and Einstein's equations. So he has this paper called the derivation of Maxwell's and Einstein equations. So what he did in this paper is that if you have Einstein's theory, the Einstein reproduction, like that, then you can show that the small fluctuation of the metric around flat space give rise to massless spin-2 particle. That is that the equation, wave equation for massless symmetric traceless rank 2 tensor. He showed the converse in this paper. He showed that, well, he's a particle theorist. He didn't like Einstein's sort of sophisticated geometric formulation of gravitational theory. So he wanted to say, well, can we do something more down to earth? Suppose that, suppose you're a particle theorist and want to construct a theory of gravity. Okay, so what would you do? Well, you try something that Yukawa did, which is to postulate a new elementary particle which mediate force. Okay? But there are various things that constrain you. So if you have scalar field, particle exchanging force, well, that seems to work. But there are things it's not consistent with the property of gravity. If it is a spin 1 particle, then it's a problem because so typically what happens is that if you have scalar particle exchange or spin 2 particle exchange, like charge attract each other. If you have a spin 1 particle exchange, like charge repel each other. So that's why, for example, in the Maxwell theory, if you try to have like charge together, the Coulomb force actually repel each other. Opposite charge attract each other. The gravity works in a different way. For gravity, all the positive energy attract each other. So it cannot be spin 1 particle. So it should be spin 2. So supposing you want to construct a theory of spin-to-mass theory in which the force is mediated by massless spin-to particle. Okay, he showed in this paper that you have to have this theory if you believe that in such a theory the low energy interaction between the massless spin-to particle should be exactly that of this Einstein. The one that's derivable from Einstein-Hill reduction, which is that to say that you substitute this into this action and expand into H. The leading term is a kinetic term. The next term is the interaction term. So you can derive interactions between this spin-to particle from Einstein's theory. He pointed out that consistency of the theory already determine what kind of interactions are allowed. And that's exactly the same as this. So that's what he showed. So what it means is that if you have massless spin particle, and in this paper he has actually, in all this kind of paper, you always make some assumptions about the theory. So but in all these assumptions that he makes, the string theory satisfies. So his theorem actually applies to string theory. So what it means is that this already shows that the string theory contains gravity. Okay. So this is very interesting. So because it took people 9 years after Weinberg's theory paper to actually discover that string theory contains gravity. And it was first done by, actually 8 years. It was first done by Miyaki Oniya, who was actually a graduate student in Hokkaido University. And then independently discovered later by John Schwartz and Joel Sharp here. And actually they went on to propose that therefore, we should be able to construct the unification of quantum mechanics and general relativity and grand unified theory out of string theory. So, but it took people for many years to realize that string theory is actually a theory of gravity, or even though it was sort of obvious from Weinberg's theory also already, because people are trying to use in the 60s, trying to use string theory for theory of hadrons, that is the protons and neutrons and things like that. And they want thinking of application of string theory to gravity. But in retrospect, from this line of thought, it should have been obvious that the string theory contains gravity. Okay. So it's very interesting that the sort of consistency of string theory automatically give rise to the emergence of string theory. Okay. And so that's symmetric tensor plot. And then there are other things. And so unsymmetric part. So unsymmetric part. So let's call it, so I keep writing this symbol is a little bit awkward. So let me write B mu nu. So I define this to be unsymmetric part of this first excitation. Okay. So B mu nu is therefore the same as B mu nu plus del mu lambda nu. So this theory has this gauge transformation. Okay. And then satisfies the equation more like by the massless. So it satisfies this equation in some case, but this is the condition. So this should be sort of very similar to Maxwell's theory. So Maxwell's theory has gauge field A mu, and A mu is equivalent to A mu plus del mu lambda. So this shows that A mu is by itself is not a physically observable quantity because it's not gauging value. It changes by change of the gauge. So there are two things that you can construct out of gauge field. So one is a field strength F mu, which is del mu A mu minus del mu A mu. So since you are taking asymmetric product sum, so it's a different. Since you are taking this minus this, so you can easily see that under this gauge transformation, this is invalid. And So you probably have taken some advanced course of electromagnetism where you have seen that this contains electric field and magnetic field in the relativistic formulation of Maxwell theory. And so therefore these are observable. This is not observable except for a situation like when the spacetime has non-trivial topologies, where if you integrate gauge field around some cycles, then it is gauge invariant, but you can also express it in terms of field strengths. So anyway, so this is gauge invariant thing. And then Maxwell theory can be expressed in terms of this. Maxwell equation can be expressed in terms of F mu. That is a very interesting duality between F mu nu and F mu nu tilde is equal to epsilon mu nu rho sigma, F rho sigma. Because if you use this, then the Maxwell equation can be written in this way. Okay, so this is the Maxwell equation. I guess this is the first set of Maxwell equations. This is the second set of Maxwell equations. So you can formulate Maxwell theory in this way. So you can see. So you can see, as you can see, this is very similar to Maxwell theory, except that what is A mu has now two indexes. And so the natural thing, therefore, is to consider the field strength H mu nu rho, which is a totally unsymmetric combination of this thing. Okay, so this is totally unsymmetric in mu nu rho. And so this is analog of F. Okay. By the way, it's very natural that such a thing appears on the in string theory for the following reason. So Maxwell theory, if you have electrons, then the electron couples to the Maxwell speed in the following way. So suppose this is the trajectory of electron. So let's map this trajectory of electron as x mu s, where s is some parameter which goes from 0 to 1, for example. Right? So then the Lagrangian, the action for the Maxwell theory can be written as b-dimensional integral of, I'm sorry, here I was assuming it's 4-dimensional, but in general it's b-dimensional, of E square, F mu nu square. But then there is a coupling of gauge field to the electron, which is characterized by this integral, A mu x dot mu dx. Right. So because Maxwell potential, the gauge potential A mu has one space-time index mu, so you can integrate this along the trajectory of electron, and then you have this natural coupling. This B field naturally coupled to string. Because the propagation of string is now give rise to a two-dimensional sheet. It's called world sheet. So this is called world line. World line. The world sheet. And so this direction goes to sigma 1. This direction goes to sigma 0. So it's, and then there's a natural coupling between B mu nu and the world sheet, because you can now integrate d sigma 0, d sigma 1, B mu nu, del sigma 0 x mu, del sigma 1 x mu. Okay, so this is a very natural thing to do. And so now you can integrate. So just like you integrate a mu here, you integrate b mu nu on the worksheet. And so this gives rise to a coupling of b mu nu. So if you have a string, so just like the gauge field is a very natural thing to couple to charged particle, b mu nu is a natural thing to couple to string theory. Okay. And then equation motion for this is given by the del mu h mu nu rho, and then also del mu g mu nu h mu rho sigma is equal to 0. So this is the analog of this Maxwell. Okay. So these asymmetric tensors are also collectively called axions. This is actually very naturally related to axions. So let me just briefly mention. So this goes a little bit away from string theory, but let me mention that. So let's forget about string theory for now. So let me talk about some puzzle about the QCD. So if you ask particle theorists how many adjustable parameters you have in standard model particle physics. Some say there are 18 parameters, and some say there are 19 parameters. So there is this one mysterious parameter that people disagree with. And this is called theta parameter. So this is a funny parameter, which is the following things. So QCD is a theory of SQ3 gauge theory plus quarks. And the gauge field is in the fundamental representation of SQ3. Quarks are in the adjoint representation of SQ3. And then there is a Maxwell, so there is a non-abelian gauge field A mu, which takes value in SQ3 adjoint representations. And then the gauge field is del mu A mu minus del mu A mu plus commutator of A mu A mu. Okay, and then the Lagrangian for the QCD is by Yang-Mills coupling QCD squares trace over the representation space of SU3 of F mu nu, F mu nu. So this is a standard Lagrangian density of the QCD theory. But there's another parameter you can introduce, which is called theta parameter, which is actually contracted by epsilon symbol. The totally unsymmetric tensor in 4 dimensions of F mu nu, F rho sigma. This is totally valid thing to write down in QCD and give rise to non-trivial interactions. This is renormalizable, so we are entitled to include that in the standard model. But one of the puzzling features that this term explicitly breaks the parity by this introduces the parity, the CP vibration. This term breaks CP symmetry, the charge conjugation and parity. Okay, so this is very puzzling because CP is broken indeed in the standard model, and it has been observed, but it's broken in a very, very tiny fashion. If theta is of order 1, this actually wildly breaks CP symmetry and give rise to all kind of funny things like electron dipole moment, etc. So there's actually a very severe constraint on the upper bound of theta. And many theorists believe that theta is equal to 0. Although you should never trust theorists, because theorists used to believe that cosmological constant is 0 too. But until you prove otherwise. But anyway, so this is a very puzzling that this is so small. It's called CP problem, strong CP problem, because if theta is not zero, then a strong interaction would break CP. So one of the, oh, by the way, that we could also write down something like that in Maxwell theory. But in Maxwell theory, this term is trivial because you can actually show that such a term is totally derivative. And so therefore, it doesn't give rise to any meaningful interaction. But in QCD, this does introduce meaningful interaction and the difference in gauge symmetry. And so this is relevant. Okay. So people have proposed various possible mechanism. Theorists are not lacking ideas. So one of the actually leading ideas is called axiom. So in the spirit of Einstein, that there are no adjustable parameters in nature, the axiom theory postulates that theta is not adjustable constant, but it's actually expectation value of some field. Namely, there is a field called axiom, which whose expectation value is theta. So there is a field theta, which is massless, or almost massless, and then the expectation value is theta axiom, theta QC. But non-perturbative effect gives rise to potential for theta, and that potential drives the expectation value of the theta to be zero by potential, by non-perturbative potential. So this is a scenario that people propose to sort of explain why theta is small or possibly zero. Okay? So that's a leading idea. Now, what this has to do with this? Well, in 4-dimensional, actually, axiom can also be described by unsymmetric tensor for the following reason. So, in Maxwell theory, there is a field strength F mu nu, but there is also F mu nu tilde, which is dual. And as you can see in this Maxwell equation, there is actually symmetry between these two equations. Right? So you can express Maxwell equation this way. And in fact, the duality is more interesting if we introduce a source. So if you have Maxwell theory, there is a source. So normally you write the Maxwell equation in this way. Oh yeah, this is the electric current. There is no corresponding current for this equation, but you could consider introducing it. And this becomes a current for magnetic monopole. So this is a magnetic current. Normally, we don't consider this because this term would be present only if there are magnetic monopoles present. So since in our observable part of the universe, we have so far only observed electrically charged particle, but not magnetically charged particle. So we can set this safely to be equal to zero for practical applications. But many grounded field theory predict existence of magnetic monopole. So in principle, you can have this. So that means that these two equations are totally symmetrical. So these are called duality. There's a duality between F and F tilde, and duality between magnetically charged particle and electrically. There's a duality between electric charge and magnetic charge and F union. So, but in 4-dimensional, it turns out that the F and F tilde are both rank to unsymmetric tensor. But this is just a coincidence in 4-dimensional where 2 plus 2 is 4. Okay, but what are the other two numbers that give rise to 4? Well, there are other combinations. 2 plus 2 is 4, but 1 plus 3 is also 4. Okay? 1 plus 3 is also 4. Okay, so 1 plus 3 is relevant for QCD because, well, so if you have unsymmetric tensor, you have 3 forms. If you have axiom, you can actually consider C mu, which is derivative of theta. So this is a 1 form. And so 1 plus 3 is again 4. So in 4-dimensional, action is actually dual to unsymmetric 3-fours. So so you can actually write down the following equation. So you can define H mu nu rho to be del mu. So I'm not going to repeat. So you have H mu nu rho sigma here, right? And so we have this equation, but we can suppose you consider dual. So how do you define dual? Well, we're going to contract this. We're going to first raise the indices, and then we're going to contract this as mu nu rho sigma, mu rho sigma, and define this as C mu. Okay, so you have C mu. So suppose you have H 3, 4, and then but H satisfies this equation. H satisfies this equation. So what does it mean? So the first equation, so this equation means you can write that this equation in terms of C. So this equation means, well, so first of all, we are going to convert this, and we should write the so H mu nu rho sigma is equal to I think it's 3 factorial, so 1/6 of epsilon mu nu rho sigma del sigma C sigma. Let's see, is this correct? I think it's correct, right? Because if you do it twice, or maybe that's a sign, but if you do it twice, then you are contracting epsilon with epsilon. So for fixed sigma, there are 3 factorial choice of indices. So you should divide it by 1/6. So if you substitute this into here, then what you find is the first equation is del mu epsilon mu nu rho sigma C sigma is equal to 0. And the second equation is del mu. Actually, second equation turned out to be this. The first equation is equivalent to del mu C nu minus del mu C mu is equal to 0 because you are contracting epsilon symbol with mu and sigma, and mu and rho's are free, but they can be arbitrary value, and you can show that this is equivalent to this condition. This condition means that you can write there is some theta such that chi mu can be written as del mu of theta. You can easily see that if chi mu is written as derivative of some theta, then you can solve this equation. So this is easy, right? If chi mu is written as derivative of theta, you can write. There's a converse, which is very well known in mathematics, called Poincare lemma. It's relatively easy to prove, although I don't have time to prove it. But if you look at any textbook of differential geometry, then you'll find it. So these are equivalent statements. So that means chi mu is the derivative of mu, and the second equation implies that box of theta is equal to 0. So therefore, the unsymmetric 3-form theory of unsymmetric 2-form gauge field is equivalent to the theory of massive scalar field. But there's one more thing, which is that the relation between them involves set epsilon sigma. So that means that if H is a standard B form, theta defined in this way is not a standard scalar field, but it's actually pseudo scalar field or pseudo scalar. Thank you very much. Or pseudo scalar. Which means that under parity transformation, it should change the sign. And this is expected for axiom because the QCD axiom, sorry, QCD theta term was of this form. Right? And so if you do the parity transformation, epsilon changes the sign. And so theta changes the sign in order for this to be invariant. And so that means that theta should be pseudo-scale. You don't want this to be, so you want this to be break CP, but if you don't want this to break parity, if this breaks parity, it's actually violate. Why they contradict with what we know about the standard model? So it should be pseudo-scalar. And so that's consistent. So this is sort of one of the reasons why this is actually a very interesting feature of string theory. So string theory give rise to the bosonic string theory in this case give rise to three types of massless field in the first excitation, and all these three fields are very interesting. So there's the graviton. And then there's a dilaton whose expectation value controls the coupling constant. And there is an antisymmetric two-form gauge field, which is actually dual to pseudo-scalar field and potentially a candidate for this axiom. So all these have very interesting features. Okay, so any questions so far? Okay, so what I'd like to do is, so of course I can go on to discuss higher excited states, but let's stop the analysis of string spectrum for now. Let me try to develop the variety of theory out of this. First direction I would like to go is generalize this to superstring. So after all, Bosonic string is actually not a good theory to begin with. It's just tachyon. So I'll show you that if you actually supersymmetrize the whole framework, then actually you can remove tachyon and you can have more reasonable spectrum. There are a variety of construction like heterotic string, which give rise to gauge symmetry. And then I would like to go on to discuss how to, so these theories, so just like bosonic strings defined in 26 dimensions, superstring theories defined in 10 dimensions. So we need to compactify the theory to give rise to 4-dimensional space-time. And then we need to introduce a notion of Calabi-Yau manifold to do that. And then I'd like to explain how Calabi-Yau geometry encodes various features of elementary particles in 4-dimensional space-time. And those include all the ingredients to construct standard models, such as generation of quarks and leptons, gauge interaction between them, and Higgs mechanism to break symmetry. So I'd like to discuss those things. But all this requires, as a preparation, the notion of conformal symmetry and conformal field theory in 2 dimensions. So I'd like to maybe spend this reminder of this lecture and maybe the beginning of this lecture just to tell you a little bit about conformal field theory in 2 dimensions. So the string words field theory is an example of conformal field theory. So conformal field theory is a quantum field theory with scaling values. And in the case of string worldsheet theory, the Lagrangian density is del x mu, eta mu nu. And this is a massless scalar theory. And since it's a quantum field theory, you need an energy momentum tensor. And the ZZ component of energy momentum tensor is del mu. Well, del mu, eta mu nu. Okay, so this is a worldsheet theory is an example. So in general, CFT is a quantum field theory with conformal invariance. So what does conformal invariance mean? Well, conformal invariance means the following things. So in general, if you have local quantum field theory, you should be able to put the quantum field theory in any curved space-time. So QFT can be defined. So for simplicity, so far we are considering the situation where both space-time and worldsheet has Lorentzian signature metric. But in studying quantum field theory, it is often useful to whip rotate the time to make the coordinates to be all Euclidean. And we can always, so as far as Hamiltonian is positive definite, you can always go back to the Lorentzian signature. So let's consider a situation where cell is defined in Euclidean signature space. And so then it can be defined on a curved space. With metric, non-trivial metric, G near nu. And it is possible because the theory has metric, theory has energy momentum tensor. In fact, the energy momentum tensor can be defined as a response to the change of metric in the following sense. So what is quantum field theory? Well, quantum field theory is a rule to calculate correlation functions, if you like. So you have a set of operators, and one should be able to calculate correlation function. So this is a sort of quantum field theory giving you a set of rules to do that for a given method. Now, so you may be interested to know, well, how this correlation function depends on the choice of metric. So for that, you may consider taking functional variation with respect to the metric. So one definition of the energy momentum tensor is that this is equal to square root of z times energy momentum tensor defined inserted here. Another way of saying it is that if you have action, which is an integral of Lagrangian density with a variety of fundamental fields and metric, then the energy momentum tensor can be defined as a variation, functional variation of the action with respect to the metric. So this is one definition of the energy momentum tensor. There are various different definitions, but this is sort of very useful definition. You can actually show, you can also, of course, introduce energy momentum tensor by just staying on the flat Minkowski or flat Euclidean space and use Noether theory. If you have quantum field theory in Lorentzian signature space-time, then there is a Lorentz symmetry, and translation symmetry, you have Poincare symmetry. So there is if you apply Noether theorem, there must be a conserved current which is associated with the symmetry. And the energy momentum tensor can be introduced as a Noether current associated with the symmetry. But you can also define energy momentum tensor as a variation of the action with respect to the background metric. And you can prove the equivalence of these two states. So sort of straightforward things, probably something to be covered in quantum field theory course. So this is definition of energy momentum tensor. And because you have energy momentum tensor, because one of the postulate of quantum field theory is that you have local energy momentum tensor. Because of that, the theory can be defined on any curved manifold because the energy momentum tensor controls the response to the change of metric. So if you define the theory on one metric, you can basically change the metric by doing this repeatedly, right? Because if you know how to take the derivative, you can integrate, and then you can change the metric. So that's why you can define the quantum field theory on any metric. Okay? What the conformal symmetry means? The conformal symmetry is invariance under G mu nu goes to e to the 2 pi of x of G mu nu. So it's a local scale transformation. There's another thing called scale invariance. The conformal invariance. There is also things called scale invariance, which is the case when phi is constant. Okay. There is a question. There is actually a very important question in quantum field theory of whether scale invariance implies conformal invariance. This was actually proven by Joe Polchinski in the late 80s in the case of two-dimensional quantum field theory. So in two-dimensional quantum field theory, you can actually prove that if the theory is scale invariant at the global scale symmetry, then you can, the theory is invariant at the local quantum. This seems like obvious thing one could have expected because quantum field theory is a local theory. All the observables are defined locally. So it should be the case, but it's actually highly non-trivial to prove this. In 4-dimension, so it took like 20 years to have that to be proven in higher dimension. In 4-dimension, it was proven by Shubimar and Komárowski about 10 or 15 years ago or so. And but there are also some counterexamples in the trivial sense. For example, 3-dimensional pure Maxwell theory is scale invariant, but not conformal invariant. So there are some counterexamples. So this is actually an interesting question. So, but when you say conformal field theory, we mean theory which has local scale invariance. So if you have local scale invariance, then what this means is that so I might have lost. How can it possible? I lose my notes. But anyway, so what it means is that if you vary in the correlation function or action with respect to metric, it gives rise to energy momentum tensor. The theory does not change if you shift it in the direction of overall scale. So that means that the variation of the metric in the direction which changes the overall scaling of the metric should be trivial. Should be trivial. So this means that the trace of energy momentum tensor should be equal to zero. So therefore one can say that conformal field theory is a theory for which you can actually define energy momentum tensor to be traceless. So you can also define it in this way. So equivalently, you can also say the quantum field theory with T mu nu such that the trace is equal to zero. Okay, so it's a symmetry. It's a symmetry. So that means that it gives rise to variety of conservation rules and algebras that realized on the action. So you can ask what kind of things that you can possibly have. Well, so in the case of in the case of Poincare symmetry or Lorentz symmetry, what was important was to look for. So let's remind. So Poincare symmetry. So if you didn't know what Poincare symmetry is, how you could have discovered it? So one way to discover it is that it's a coordinate transformation. Infinitesimal coordinate transformation preserving the Minkowski method. Right? So that's sort of definition of Poincare symmetry. And under coordinate transformation, the Poincare metric transforms del mu. Well, I guess epsilon should be included in sigma. Del mu sigma nu plus del mu sigma mu. And so therefore, if this is equal to 0, then that means that del mu sigma nu is equal to this should be equal to 0. So that means that you can write down sigma mu to be something unsymmetric plus constant, where C mu nu is unsymmetric, and C mu, and then these are constant. And this shows this reproduces a Poincare symmetry because this corresponds to translation, and this corresponds to rotation and Lorentz boost. Okay, so so this you can reproduce Poincare symmetry this way. So we can try to play the same game for conformal symmetry. So in the case of conformal symmetry, what should we do? Well, so in that case, again, so if you make this change of coordinate, the metric will change like this. Now, for general metrics, you should use covariant derivative like that. Now, in the case of Poincare symmetry, we require this to vanish because we want to preserve the metric. But in conformal symmetry case, we are not that strict. We only require the metric to be preserved modulo of our scale, because even if you change the scale, even if we rescale the metric, the theory does not change. So that means that the requirement for the conformal symmetry is that this is proportional to G mu nu. Right? So you can ask how many C's can we have? So here I gave you a complete solution to this problem. So you can ask how can we do this? Well, first of all, we need, so if I said this is proportional to G mu nu, but we need to change and fix the coefficient. So what is this? Well, del mu C mu plus del mu C mu is proportional to G mu nu, so let's write it as C. But we can then determine C because we can take trace of both sides. So you can write down G mu nu, del mu C mu. There are two of them, so I put 2 here. Is equal to C times the G mu nu, G mu nu. But if the space-time is D dimension, this is D. And C. So that means that C is equal to 2 over D of divergence of C. So therefore, the condition is that this is equal to D over 2 G mu nu divergence of C. So therefore, the conformal symmetry is a solution to this equation. Okay. So you want to solve this equation. Okay, so you can ask, well, how many solutions are there to this equation? Okay. So in D dimension, for D greater than 3, there are finite dimensional solutions, space of finite dimensional space of solutions. Because in fact, you can see that the number of equations, there are more equations than number of solutions. So you can easily guess that for sufficiently high dimension, you have more equations than solutions because C is a vector. So that means that number of independent variables is D, right? But here, so how many equations do we have? Well, we have symmetric tensor. It's traceless because I chose it so that this has no trace. So that means that symmetric, we have D plus 1, number of equations, the minus, because it's traceless. And but it's grows quadratically. Grows quadratically. And the number of variables is D. So this can be, well, you can actually calculate the difference. So let's calculate this. So let's calculate this difference. And this is equal to half of D squared plus half of D minus 1. And then you have minus 1, so you subtract the minus 1. And so when does it become 0? So you have D squared minus D minus 2 is equal to 0. So this is D minus 2, D plus 1. That's correct. So that means that actually I should have said greater than 2 because you see that well, so this means that when D is greater than 2, then this is positive, right? So you factorize like that. So you can see that this is greater than 0 for D greater than 2. So this is the number of equation. This is the number of variable. So for D equals 0, D greater than 2, therefore there is a finite number of solutions, finite dimensional solution. In fact, the space of solution to this equation gives rise to a manifold. And so for Euclidean Lorentzian signature, it's O2, comma D. And Euclidean is O of 1, comma, oh, sorry. So spatial, so it depends on the type of metric. Dimensional solution for Minkowski metric, it's O of 2, comma D. And for flat Minkowski Euclidean metric, it's O of 1, comma D plus 1. So anyway, so you have this many finite dimensional space. Yeah. So anyway, so this is useful because it has bigger symmetry than Poincare symmetry. So it's constrained the correlation function somehow. And in recent years, in the last 10 years or so, there have been enormous development in understanding conformal theory. Professor David Zappin, for example, at Caltech is an expert on that subject. For D equal 2, something interesting happens. Because the number of equations is the same as number of solutions. For D equal 2, the number of equations is number of variable. Because for D equal 2, this is 2. There are 2 equations for 2 variables. So you can have infinitely many solutions. So in fact, conformal symmetry in 2 dimensions is infinite dimensional. Because so you can easily see that by rewriting this in and the interesting thing is that this is true for any curved space, not just flat space. So well, I shouldn't say it, but so I need to clarify it. But let me first state it. So what it is. So suppose I choose a metric. So in 2 dimensions, you have 2 by 2 metric. But let's suppose for simplicity, let's consider Euclidean case. So we can do the same thing for Lorentzian signature case. Uh, we can choose a metric to be diagonal. So ds squared. Because you have so you have three components of the metric, so we can use coordinate transformation to diagonalize it. So we can, without loss of generality, we can always write this in this way. Or you can also write it in this way, where z is x plus iy, and z bar is x minus iy. Okay, and so in this coordinate, z component is 0, and then z bar is z bar z is equal to 1/2 of v to v. Okay, so we can choose this coordinate, and then we can ask, well, how does the metric look like? How does the equation look like? Well, so if you calculate del z cz, this equation, then we have del z cz. And then off-diagonal component is 0. So that means that this is 0. And similarly, del z bar, cz bar, plus del z bar, cz bar is equal to 0. So how about the this one? Actually, this becomes trivial equation because this is equal to 2/2. And you get gzz, which is this. But you can actually do that calculation and find that this is actually exactly this. So this is actually trivial because this is cancelled by this. So this is trivially 0. So the non-trivial equation in 2 dimensions are these two equations, which is del z cz is equal to 0, and del z bar cz bar is equal to 0. But it's not a difficult calculation to show. But so this is a covariant derivative, so it has Christoffel connection in it. But it's actually simple calculation to show that this is actually equal to g z z bar of del z of cz bar. So by taking out the metric, you can actually show that this is actually ordinary derivative with z. So in 2 dimensions, therefore, this is by the way called the conformal Killing equation. This is called the Killing equation. These kind of equations are called Killing equations. So the equation for the coordinate transformation which preserves the metric. And this is called conformal Killing equation because it's equation for the coordinate transformation which preserves the metric up to rescaling. And the conformal Killing equation in 2 dimensions can be written in this way. So that means that any holomorphic function is a candidate for coordinate transformation, which preserves the metric modular coordinate, modular rescale, and similarities. Okay, so clearly there are more symmetries in 2 dimensions, and in fact, the Virasoro algebra that we have been discussing to impose physical state condition for string excitations are exactly the data charge associated to this symmetry. So in the next lecture on Wednesday, I'll tell you a little bit more about conformal symmetry, and then go on to discuss the generalization of bosonic string, superstring, heterotic string, etc. Okay, so thank you, and see you on Friday, on Wednesday. Sorry.
这种物理